Welcome to lecture number 7. So, in this lecture, we will cover the transient analysis, basically the DC transient analysis of a first order RL series circuit. Okay. So, first of all, we have to know that what is transient. Look, in every circuit, if we switch on the supply at a certain time, suppose t is equal to 0, the current and voltage, these two parameters, do not reaches its final value immediately after switch on the supply, that is t equal to 0. Okay, so that it takes some time to reaches its final value, that is the steady value. So this time is basically known as the transient. That means if we suddenly switch on the circuit at t equal to 0, the current and voltage do not reaches its final value or steady value at that t equal to 0. It takes some delay, some times to reach its final value. So within that period, that means the transient period, the value of the current and voltage is called the transient value, right? Similarly, if you think in this way that at certain time t equal to 0, if we switch off the circuit, that means if we disconnect the supply, so again the current and voltage do not fall down from its final value to the initial value. Again it takes several times or some times to fall down its initial value after the switch of the supply at t equal to 0. So again in this way we can also define the transient. One is during switch on and another one is during switch off. It is basically the transient, right? So now, we are going to discuss about the transient analysis of the series RL circuit, first order, in this lecture. So first of all, this is the lecture number 7. Okay, so the lecture is all about transient analysis of first order series RL circuit. It is basically the DC transient analysis. Okay, in this lecture we are going to discuss about the DC transient analysis. That means the supply voltage is DC. Okay, so the circuit will like that. Suppose if we draw the circuit, so this is the DC supply voltage, and with this one resistance and one inductance connected in series. Okay, so this is the supply voltage V, and from the supply voltage, suppose I current is flowing, and this is R and this is the L. Okay, so this is plus, this is minus, and again this is plus, this is minus. So across the resistance there will be a voltage drop called VR, and across the inductance there will also be a voltage drop called VL. Okay, so if we apply simply a KVL in this circuit, so what we can write? We can write V minus VR minus VL, that is equal to 0. This is simple like the equation. Okay, so from that equation we can write VL, that means the voltage across the inductor will be V minus VR. So that means V minus, so what is VR? That means the voltage across the resistance, that is the simply the current into resistance across as per the Ohm's law. So V minus I into R. So now the voltage across the inductance can be written as VL is equal to L di dt. Very simple. So that is equal to V minus IR. So if we arrange the equation in this way, like that, di by V minus IR, so that is equal to 1 by L into dt, right? So now if we integrate this equation both sides, that is if we integrate this equation, So after integration, what we can write? So it is simply di by vy minus I into r. So that means the log term comes here. That means the minus ln v minus ir, but the term I is actually associated with the r. The product of I into r is present. So that means for that it is again 1 by r is present. Okay, because the term is ir, di by v minus ir. So for ir it is 1 by r comes. Okay, and then plus some constant, the integration constant, that is equal to 1 by l into t. Right, very simple. So now if we put the initial condition, what is the initial condition? That means if we put the initial condition, what is the initial condition? That means at t equal to 0, the current is 0, because at t equal to 0 means when the supply voltage is not connected. So at that moment current is also 0. So this is the initial condition. Now if we put the initial condition, so what we can write? Simply we can write minus ln v by r, because ir terms is 0, because I is also 0. So minus ln v by r plus k, that is equal to 0, because t equal to 0. So we can write that k equal to ln v by r. So at initial condition we can derive that the integration constant k is equal to ln v by r. Okay, so now if we put the value of k at this equation, that means at this equation, so what we can write? So we can write minus ln v minus ir into 1 by r. Okay, plus k. So what is the k? K is ln v by r. Okay, that is equal to 1 by l into t. Right. So from this equation, simply the property of logarithm, that is log a minus log b. So that is, we can first of all we can arrange in this the equation in such a way, that is suppose ln v by r. Okay, so we can write this in this way, that is ln v into 1 by r. We also can write this. So if we take 1 by r common, so it is like that ln v minus ln v minus ir and whole common 1 by r. So that is equal to 1 by l into t. Okay. So next, the property of logarithm, log a minus log b, that is equal to log of a by b. So we can write ln v by b minus ir log a by log b, that is equal to, we can write r by l into t. So up to this I think it is clear. Okay. So next, if we inverse the equation in both sides, so that means we can write ln v minus ir by v. Okay, that is equal to, here the minus sign comes, minus r by l into t. So if we replace the logarithm term, so it can be written as like that, v minus ir by v, that is equal to, this is the anti-log, that means e to the power minus r by l into t. Okay, so further if we simplify this, we can write 1 minus ir by v, that is equal to e to the power minus r by l into t. Okay, so that means if we change the position of e to the power minus r by l into t in the left side of the equal to, so we can write 1 minus e to the power minus r by l into t into v, that is equal to I into r, that means equal to the voltage across the resistance VR. Okay, so here is the another, here is, this is the one type of the equation. So v equal to that means V suffix the voltage across the resistance will be V into 1 minus e to the power minus R by L into T. And again we can represent this equation in such a way that from this equation you can write I equal to V by R 1 minus e to the power minus R by L into T. So it is the equation of current. It is the equation of current of the series RL circuit. Okay, when we switch on the supply, that means if we switch on the supply at t equal to 0, so that means actually there is a small mistake. That means if we consider the switching on time, so here the circuit will like that in this way. That means there is a switch basically. So there is a switch. Okay, so the switch is closed, that means switch is turned on at t equal to 0. So this is the V, this is the current I, and this is the switch. Okay, so this is the switch. So at t equal to 0, the switch is closed. Okay, so at t equal to 0, switch is on. So at t equal to 0, switch is on, then the transient analysis of the circuit will be in the following manner. Okay, like that. So we have already got the equation of the voltage across the resistance and the current. So now if we look about the inductor voltage, so we have already got that the inductor voltage VL is equal to V minus VR as per the KVL equation. So now if we substitute the value of VR in this equation, so what you can write? VL equal to V minus V into 1 minus e to the power minus R by L into T. So that means the VL will be V e to the power minus R by L into T. So this is the equation of the inductor voltage. Okay, so make it a box. Actually we will try to remember these three equations: the voltage across the resistance, the voltage across the inductance, and the current. So this current is mainly known as the charging current. When the switch is on, the inductor is starts charging, okay, with this current, right? So the inductor voltage will be V e to the power minus R by L into T. Okay, so the inductor voltage can be represented in such a way that the VL take a different color. So VL will be V e to the power minus T by tau, where tau equal to L by R. So what is tau? The tau is known as the time constant. Okay, the tau is known as the time constant. So I will go to the details. What is the time constant? So before that, I will make a table. With this quantity, that is the first one is the VR, the second one is the VL, the third one is the I. Okay, so put it on left side. Okay, so we will consider about the timing, that is at t equal to 0, at t equal to infinite. So make the table in this manner. So at t equal to 0, if we look into the equation of VR, if we look into the equation of VR, so VR, here it is, VR at t equal to 0, what is the value of VR? So put t equal to 0, so VR will be 0, okay, and t equal to infinity, put t equal to infinite, that means e to the power minus infinite, so that is VR equal to V, the supply voltage V. V will be the supply voltage, the DC supply voltage. So at t equal to 0, VR will be 0, at t equal to infinite, VR will be V, supply voltage V. Again, if we look into the equation, that is VL, so this equation, okay, if we put t equal to 0, so t equal to 0, e to the power 0, that means 1, so VL will be the V, exactly equal to the supply voltage though. So at t equal to 0, VL will be V, and at t equal to infinite, that means e to the power minus infinite, that means 1 by e to the power infinity, that means 1 by infinity, so it is also 0. That means at t equal to 0, the inductor voltage is V, and at t equal to infinite, the inductor voltage is 0. So it is V and it is 0. Okay. Now the expression of current. So in this expression, if we put t equal to 0, that means e to the power 0, that is 1, e to the power minus 0, that means 1 by e to the power 0, that means 1. So 1 minus 1, it is also 0, that means I equal to 0. Clear? Okay. Simple. This is if we put the value t equal to 0 and calculate, you will find the correct answer. I am not going into the details. Okay. At t equal to 0, I equal to 0, and if we put t equal to infinite, we get I equal to V by R. Okay. So this is the table. These value are required to plot the graph. Okay. So if we plot the graph, so it will like that. Let me draw the graph first. So this is actually very difficult to draw in this digital platform. Still I am trying. Okay, so this is the time axis, and suppose this value is V. You can assume this value is V, supply voltage V, and this is a 0. Okay, so if we first plot the graph of VR, okay, so take 3 different colors. Suppose I take the first blue color to represent the VR. So VR at t equal to 0, VR will be 0, so it is 0, and at t equal to infinite, VR will be V. That means the graph will, and from the equation of the VR, it will like that, it is an exponential graph, that is exponentially increasing. The graph will be like that, it is exponentially increasing. Okay, so it starts from t equal to 0, and finally it will like that. Again I am saying that this is very difficult to plot in the digital platform, but still the graph will like that. Okay, so this is actually the VR. We mark it, the blue color represents VR. Okay, at t equal to 0 it is 0, and at t equal to infinite it is V. Next VL. Okay, so if I take this color to mark the VL, so at VL at t equal to 0, VL will be the V. That means it starts from the final position, it is the supply voltage position V. V means the supply voltage V. So at t equal to 0, it will start from the V, and at t equal to infinity, it will reaches the value of the initial value, that means 0 value. So, and again the equation of VL represents that it is also a exponential graph, that is exponentially decreasing. Okay, so that means it will start from the final value V, and again it will reaches the 0 value. It will reaches the 0 value at t equal to infinity, like that. Okay, so actually this is very difficult. Okay, this is like that something. So this is the expression of VL. So the green one represents the expression of VL. Now if we consider the graph of I. So we will consider the different color. It is suppose pink color. So it will represent the value of I. So I at t equal to 0 it is 0, and at t equal to infinity it is V by R. So V by R means it is a constant DC value, as V is the supply voltage, R is the resistance. So if we take the ratio of V by R, it will also a constant. So look, this magnitude is the supply voltage V. If we subtract the V with R, so similar, it is very common, the magnitude will be fall down. So if this portion is V, so V by R will be, suppose I am drawing, suppose this position is V by R, this position is V by R, this up to this magnitude. Okay, that means if we draw a dotted line in this manner, so that means the current starts from the 0 value, that is I starts from the 0 value at t equal to 0, and it will reaches V by R at t equal to infinity. So the graph will like that. Okay, it start from 0 and it will reaches V by R at t equal to infinity. Very simple. So this is the representation of the DC transient analysis in graphical method, the inductor voltage, the voltage across the resistance, and the charging current. Okay, so now there is an interesting thing from that graph. We will find out the value of time constant. Okay, so if we consider at t equal to tau, at that moment, suppose at t equal to tau, so what we can write at t equal to tau, the current will be, if we put the value t equal to tau at the expression of current, tau means L by R. Okay, so that means R by L into L by R, so e to the power minus 1, that means 1 by E, 1, so V by R into 1 minus 1 by E. So it will approximately, that is 63.2 of V by R. If we put the value of tau in this equation, tau equal to L by R, that is R by L into L by R. If we okay, I am going to details so that you will not face any difficulties like that. So I equal to V by R. Okay, V by R into 1 minus e to the power minus R by L into tau. Okay, into tau. So that means I equal to V by R 1 minus e to the power minus R by L into L by R. So from that equation we can write I equal to, L will be cancelled, so 1 minus e to the power minus 1, that means 1 minus 1 by E, and we further calculate, putting the value of E, we can write V by R of 0.62. That means from that equation we can tell that the time required by the current to reaches 63.2% of its steady value is called the time constant. Okay, that means if we take the percentage, it will like that 63.2% of V by R. V by R means the steady value, the steady DC value. That means the time required by the current to reaches its 63.2% of the steady value is called the time constant. So from this equation we will define the time constant. Clear? Okay, so next one interesting thing I have missed it, that is we have marked that tau equal to L by R. Okay, for the series RL circuit. So it is actually known as a time constant. So very simple that the unit of time constant is also, it should be time, right? The unit should be time. So if anyone gives you a question that prove that the unit of time constant is equal to time, how you can prove it? It is actually very tricky part, but very interesting, very simple. Tau, that means time constant, the unit should be in time, but the expression of tau is equal to L by R. So how we can prove that the ratio of L by R denotes the value of the time? Very simple. Look, we know that VL equal to L di dt, right? We know that VL equal to L di dt. That means we can write actually L into I by T. We can write that, okay? So that means L equal to V into T by I, okay? So now if we put the value of tau, so L by R, that means, so actually if we take this portion some upward, okay, so if we put the value tau equal to L by R, that means V into T by I by R. R equal to what? R equal to V by I, okay. So 1 by R equal to I by V, that means I by V. So here I and V cancelled out and only T is remain. That means T is a limit of time. So from there we can prove that the unit of time constant equal to time, okay. So unit of time constant equal to time. It is very interesting. The unit of time constant equal to time, right? Then this is the case of the switch when the switch is on. So now if we consider the portion, the source free portion, that means when the circuit is free from the DC source. So source free. Source free condition means if we draw the circuit, that means this is a DC supply voltage and the switch is disconnected here, okay. R, L, and the switch is disconnected, the switch is off. The switch is off. This is the supply voltage and this is the R, this is the L. So across R again it is VR and across L again it is VL. Like that similar thing is happened here. This is the source free condition. When the circuit is disconnected from the supply, that means the switch is off, okay. That means the switch off, right? So the analysis is same like that. If we take the KVL equation, so it is simply VR plus VL equal to 0. Now the supply voltage is disconnected, so we can write VL equal to minus VR, that means equal to L di dt equal to minus I into R. So from that equation we can write di by I equal to minus R by L into dt, and if we take the integration both side, so we can write ln I plus k, the integration constant, that is equal to minus R by L into t, okay. And at t equal to 0, that means the initial condition, at t equal to 0 we can write ln, suppose the current is I0, I equal to I0, at t equal to 0 the current I equal to I0, so ln I0 plus k equal to 0. So from that equation you can write k equal to minus ln I0, the initial condition. So now if we put the value of k, so we can write ln I minus ln I0 equal to minus R by L into t, from that equation actually. So this is the mother equation. So from that equation we can write ln I minus ln I0. So from that equation we will also write ln I minus I0, that is equal to minus R by L into T. So I equal to I0 e to the power minus R by L into T. So this is the equation of current when the switch is off. That means the discharging current. Okay, and again we can write that VL equal to minus VR. So putting the value of that is equal to minus I into R. Okay, so that means so VL will be minus I0 e to the power minus R by L into T into R. So that means the VL will be minus V. I into R means V. So minus V e to the power minus R by L into T. So this is basically the expression of inductor voltage. Okay, minus V e to the power minus R by L into T. This is basically the expression of inductor voltage, and from that equation we can write VL is equal to minus VR. So obviously the VR will be the same, but minus sign is omitted. So V e to the power minus R by L into T. So that is the equation of the voltage across the resistance VR. So now again we can write that the inductor voltage is equal to VL equal to that is minus V e to the power minus T by tau, where tau is again L by R. This is a time constant. As similar as that, next if we plot the table, again if we plot the table in like that, suppose this is first one is VR, second one is VL, and third one is I. Okay, draw the table first, and we take the condition at t equal to 0 and at t equal to infinite. So at t equal to 0, if we put the value t equal to 0 at the equation of VR, it will be exactly V, and at t equal to infinite the VR will be 0. Just put the value of t in place of in the expression of VR, and you will find the actual value. And suppose the value of VL at t equal to 0, if we put the value t equal to 0, that means the VL will be minus V here. Okay, that means the, okay, I am going to details in letters in sometime later. Okay, VL equal to minus V and t equal to infinite, the value will again 0. And in the expression of I, so what you can see, so this is the expression of I. So at t equal to 0, the I equal to I0, and t equal to infinite, the I equal to 0. So it is I0 and it is 0. Okay, so this is the table. So now if we plot the graph, so that means suppose this is a supply voltage V. Okay, this straight line denotes the supply voltage V. So the expression of VR, that means VR starts from the at initial condition, VR starts from the final value, that is V, and again it will go to 0. So if we take the blue color, so like that, so the blue one represents the value of VR. Again VL, the green one, starts from minus V, and again it will go to downwards V. So it is a VL. And current is represented by I. So I equal to V0, that means I0. I0 means actually what? V by R. So this is that portion V by R. This is also a constant DC value. That means starting from V by R, it will also go to 0. So this is the I0 or I. Okay, so this axis is known as a time axis. Look, here is a very interesting thing, that VL, when the switch is on, the VL at t equal to 0, the VL was V plus V, and when the switch is off at t equal to 0, the VL will be minus V. That means the magnitude is same, V, the supply voltage, but the polarity will reverse. That means at supply at t equal to 0, the inductor is going to charge with, and it will reaches the final value of the DC voltage plus V, and at t equal to 0, when the switch is off, it will discharge with the same voltage from the same DC voltage, that is V, but the polarity will reverse. That means it will discharge. Plus polarity means it will charge, and minus polarity means it will discharge, but the magnitude V is remains same. This is nothing else in this case. Okay, so this is the case of the transient analysis of the DC series RL circuit when the switch is off. So now here are two important things that I was forgotten to I was forget to tell, that is, when the switch is on, okay, when the switch is on, two important thing, when the switch is on, we know that the VL at t switch is on, that means at t equal to 0, okay, at t equal to 0, VL is equal to V, and at t equal to infinity, VL equal to 0. That means the VL equal to V means what? Particularly the inductor faces the supply voltage. V means the supply voltage. That means inductor is basically the open circuit, right? Think twice. At t equal to 0, the switch is on, the voltage across the inductor, that is VL, will be V. That means it faces the supply voltage. Same supply voltage is occurred across the inductor. That means inductor is basically the open circuit. There is no other voltage drop. The supply voltage is present here across the inductor. That means there is no other voltage drop. That means the inductor is basically open circuit. Okay, sorry if I shift this position, and again we can write that it is open circuit. Okay, and at t equal to 0, sorry, at t equal to infinite, VL equal to 0, the voltage across the inductor is 0. At what condition? If the inductor is short circuit, because in short circuit, at the short circuit position, in every element, it may be resistance, it may be inductance, as a short circuit terminal represents the voltage across it equal to 0. Short circuit means the high current flow through it, but the potential difference is 0 across that part. So VL equal to 0 means the inductor is short circuit. So two important conclusions are can be formed from these two equations. That means if we take some time for writing this, inductor is initially open circuit and finally short circuit. This is a very important question for any competitive exam, that is the behavior of the inductor. That means from this transient analysis we actually found what? We actually found the behavior of the inductor, the behavior of the current, charging current or discharging current, the behavior of the inductor during charging, during discharging, what they can perform, what they behave. At charging at the t equal to 0, the inductor is behave like an open circuit, and at discharging at t equal to infinity, it behaves like a short circuit. So this is a very important part in this lecture. So this is one thing, and second thing is the unit of time constant is equal to time. Okay, so
we have already proved it from the from our previous discussion, and so this is the thing. So this is all about the DC transient analysis of the series RL circuit. Okay.